Question number 20. Which one of the following has more tendency to form covalent compounds? The options are barium, beryllium, magnesium and calcium. This question can be solved on the basis of Fajan's rules. Fajan's rule says compounds having small cation are predominantly covalent. So, among these options, the atom which can form the smallest cation is beryllium. So, beryllium compounds are predominantly covalent. The answer is second option, beryllium. Let's look at the explanation. Question number 20. The order of size is B2 plus smaller than Mg2 plus smaller than Ca2 plus. This is smaller than Ba2 plus. So, among these cations, the smallest is beryllium, and due to this, the polarizing power is in the order B2 plus greater than Mg2 plus greater than Ca2 plus. This is greater than Ba2 plus. So, because of highest polarizing power of B2 plus, compounds of beryllium are predominantly covalent. That is the explanation for this. On the basis of Fajan's rules, we say B2 plus, due to its high polarizing power, will have maximum covalent nature. And the correct answer is second option, BE. Question number 21. The dipole moment of HBr is 1.6 into 10 raised to minus 13 coulomb meter and interatomic spacing is 100 picometers. The percentage of ionic character of HBr is. Let's try to solve this question. He has given the dipole moment as 1.6 into 10 raised to minus 30 and he has given HBr bond length and asked what is the percentage ionic character. Percentage charge or percentage ionic character is given by this formula, mu observed by mu theoretical into 100. Now, let's apply this. You have observed dipole moment 1.6 into 10 raised to minus 30. Mu theoretical is obtained by multiplying the charge of electron in coulombs with bond distance. So, this comes to 1.6 into 10 raised to minus 19 coulombs. This is a full charge of electron into 100. This is bond distance and this has to be changed into meters. So, this should be multiplied with 10 raised to minus 12 and this is multiplied with 100. Now, if you cancel off these two, then this 100 gets cancelled and you have answer 10%. 10 raised to minus 19, 10 raised to minus 12 comes to 10 raised to minus 31 and when you put it in the numerator it becomes 10 power 1. So, the percentage ionic character is 10%. So, the correct answer is second option 10. Question number 22. The increasing order of size of various hybrid orbitals is. Here we need to compare sp, sp2 and sp3 orbitals. So, what is the order of increasing size of these orbitals is asked. The first option is sp, sp2, sp3. Second option is sp3, sp2, sp. Third option is sp2, sp3, sp. Fourth option is sp2, sp, sp3. Now, we compare size of the orbitals on the basis of percentage S character. Remember, as percentage S character increases, size of orbital decreases. Because s orbitals have spherical shape, if you have more s character, then the size will be more spherical, so it will be smaller in size. Now, orbital percentage s character. If it is sp, then the percentage s character is 50. If it is sp2, then it is 33.33, and sp3 the s character is 25%. So you can see sp orbital has highest s character, so its size will be smallest. Then comes sp2 and finally sp3. So the correct answer is first option, sp less than sp2 less than sp3, that is the order of size of orbitals. So the correct answer is first option. Question number 23. Which one of the following possesses maximum hydration energy? Option 1 is MgSO4, option 2 is calcium sulfate, option 3 is strontium sulfate, and option 4 is barium sulfate. And the correct answer given is first option. Now let's try to explain it. We see that the anion present in these 4 options is same, so we need to decide on the basis of cation. So look at this. The order of size is Mg2 plus is smaller than Ca2 plus, smaller than Sr2 plus, this is smaller than Ba2 plus. So because of smallest size of Mg2 plus, it has maximum charge density, and as the charge density increases, hydration energy increases. So the correct answer is MgSO4. It has highest heat of hydration because of very small size of Mg2 plus, and due to very small size its charge density is high, and that's the reason for high heat of hydration. Let's look at the electronic configuration of B2. B2 has 10 electrons. The electronic configuration, molecular orbital electronic configuration can be written like this: sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2p x1, pi 2p y1. This clearly tells us that B2 is paramagnetic. So that's the reason why we rule out option 1. If you look at O2 plus has 15 electrons. You know O2 has 16 electrons, so O2 plus is supposed to have 15 electrons. Any species with odd number of electrons will be definitely paramagnetic. So B2 and O2 plus both are expected to be paramagnetic. Now let's look at C2 and O2. C2 has 12 electrons. So you can write the configuration like this: sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2p x2, pi 2p y2. So you don't have any unpaired electrons, so C2 is diamagnetic. But look at O2. O2 has 16 electrons. If you write the configuration, you realize this will be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2p x1, pi 2p y1. So this clearly tells us that oxygen is paramagnetic. So option 2 is also ruled out. Now look at option 3. In option 3 you have N2. N2 has 14 electrons. You write configuration same as B2. Only thing is you need to add electrons, 4 electrons. So those 4 electrons will enter into pi 2px, pi 2py and sigma 2pz2. So that becomes diamagnetic. Whereas O2 2 minus will have 2 extra electrons when compared to O2. Those 2 electrons go to pi 2p x1 and pi 2p y1. These 2 will become pi 2p x2 and pi 2p y2. So the third option has a pair in which both the species are diamagnetic. And look at the case of fourth option. N2 is definitely diamagnetic, we have just now seen. NO has 15 electrons, 7 coming from nitrogen and 8 coming from oxygen. It has 15 electrons. So we have said just now that when you have odd number of electrons, the species will be paramagnetic. So NO is paramagnetic, N2 is diamagnetic. So the correct answer is third option. Question number 25. In which one of the following species number of lone pairs on central atom and number of d orbitals used in hybridization by central atom is same? Number of lone pairs on central atom and number of d orbitals used in hybridization are same. Let's find out. We have various options. First option is ICl2 plus, second option is ICl2 minus, third option is IF7, and fourth option is XeF4. Let's first talk about ICl2 plus. We need to first try to find out the type of hybridization of iodine in ICl2 plus. We do it like this. We need to find out number of electron pairs. So half into V plus M minus C plus A. Here V stands for number of valence electrons on the central atom. M is number of surrounding monovalent atoms. C is charge, the magnitude of positive charge, it is coming to +1. A is magnitude of negative charge, it is ruled out because this is a positive species. Let's put the values. P equals to half into V for iodine is 7, M is 2, and there is a unit positive charge, so that has to be deducted. So P comes to 4. That means the hybridization is sp3. There is no d orbital involved in hybridization. First option is ruled out. Let's look at second option, ICl2 minus. P equals to half into 7 plus 2. This time it is +1 because the charge is negative. So it comes to P equals to 5. The hybridization is sp3d. So number of d orbitals involved in hybridization is 1. And how many lone pairs are present on the central atom? See, number of lone pairs is equal to number of electron pairs minus 2. 2 is the number of surrounding atoms, that comes to 3. So this molecule has 3 lone pairs and the number of d orbitals involved in hybridization is only 1, so this cannot be the correct answer. Whereas IF7 has iodine surrounded by 7 fluorines, it has no lone pair, all the 7 bond pairs are present, so there is no lone pair, so this is out of question. Hybridization is sp3d3, 3 d orbitals are involved in hybridization, no lone pair is present on the central atom. Look at the case of xenon tetrafluoride, XeF4. If you apply the same formula, P equals to half into 8 plus 4. So P comes to 6. This is sp3d2 hybridization. So number of lone pairs equals to 6 minus number of surrounding atoms 4. This comes to 2. So this has 2 d orbitals involved in hybridization. It has 2 lone pairs. So the correct answer is fourth option, XeF4. XeF4 has 2 d orbitals involved in hybridization and XeF4 has 2 lone pairs on the central atom xenon. Question number 26. BF bond distance in NH3BF3 adduct is dash than BF3. Here we need to compare bond length in the adduct and bond length in BF3. We are comparing BF bond length. Look at the options. First option is shorter, second option is equal, third option is longer, fourth option is double. But the correct answer is longer. Let's see how it is obtained. If you look at the structure of BF3, you have boron surrounded by 3 fluorines, and boron has got a vacant orbital. So one of the fluorines will back donate its lone pair to the vacant orbital of this is a back donation from fluorine to the vacant orbital of boron. So because of this, this will get a double bond character, but this pi bond is not localized here, it gets delocalized on the 3. So you can write resonance hybrid for BF3 as boron surrounded by 3 fluorines through single bonds, and then you have broken lines indicating partial double bond character. So the BF bond order is taken as 1.33. Now look at the adduct. In the adduct, the vacant orbital of boron is used up. It has been used in the accommodation of lone pair donated by nitrogen. So there is no scope of back bonding from fluorine to boron. So this bond order of this will be 1. So when you go from BF3 to the adduct, the bond order decreases. So when bond order decreases, bond length increases. So the bond length in the adduct will be longer. It is longer bond in the adduct when compared to BF3, because in BF3 there is a back bonding, and due to back bonding BF bond order increases, therefore bond length decreases. So the correct answer is third option. BF bond length is longer in the adduct when compared to BF3. Question number 27. Among the following compounds of boron, the species which also forms pi bond in addition to sigma bond is? We need to find out the species in which you have pi bond in addition to sigma bond. Let's write all the structures. Option 1 is BF4 minus. It has boron surrounded by 4 fluorines with a net negative charge on the species. So there is no scope of back bonding because boron does not have a vacant orbital. Now option 2 is BH3. Borane, actually this species does not exist, highly unstable species. There is no scope of back bonding as hydrogen does not have a lone pair. Number 3 is B2H6. Here also all the orbitals are involved, no lone pair is present on hydrogen, so no question of back donation. But in BF3 we know very well, we have seen just now that back bonding can take place from fluorine to boron. This gets delocalized. So this has the extra bond which is formed, the dative bond, the back bond is the pi bond. And these bonds are sigma bonds. So this consists of both sigma bond as well as pi bond. So the correct answer is fourth option. Question number 28. During the change of NO plus to NO, the electron is added to option 1 sigma orbital, option 2 pi orbital, and option 3 is sigma star orbital, and option 4 is pi star orbital, and the correct answer given is fourth option. Let's try to find out. We are changing NO plus to NO. See, we need to write molecular orbital configuration, electronic configuration of both NO and NO plus we will realize. So for NO has 15 electrons. Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, then you have sigma 2pz2, pi 2px2, pi 2py2. Up to here we have accounted for 14 electrons, that is NO plus actually. NO is 15, so we need to add one extra electron. That extra electron will go to pi star 2px. This is the configuration of NO, and the configuration of NO plus will be the same thing except pi star 2px1. This is the place where that extra electron is present. So we can say when you go from NO plus to NO, the extra electron has been added to pi star orbital. So the correct answer is fourth option. Question number 29. The paramagnetism of O2 molecule is due to the presence of 2 electrons with parallel spin in A. First option, bonding pi orbitals, Second option, anti-bonding pi orbitals. Third option, bonding sigma orbitals, and fourth option is anti-bonding sigma orbitals. And the correct answer given here is second option, that is anti-bonding pi orbitals. We need to write the electronic configuration of oxygen molecule, and we realize that these electrons actually go to pi star orbitals, that is anti-bonding pi orbitals. O2 molecule has 16 electrons. If you write the configuration, sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. This accounts for 8 electrons. We still have 8 electrons. Then comes sigma 2pz2, then comes pi 2p x2, pi 2py2. With this we have accounted for 14 electrons. We still have got 2 electrons to go. Now comes pi star 2p x1, pi star 2p y1. So these are the last 2 electrons which have gone to the anti-bonding pi orbitals. So the correct answer therefore is second option. The last 2 electrons which are responsible for paramagnetism are present in the anti-bonding pi orbitals. The star indicates that it is anti-bonding. Question number 30. The dipole moment of chlorobenzene is 1.5 dBi. The dipole moment of tetrachlorobenzene is how much? That is the question. First option is 2.86 dBi. Second option is 2.25 dBi. Third option is 1.5 dBi. And fourth option is 0. That is non-polar. And the correct answer given here is third option, that is 1.5 dBi. Let's try to find out. See, when you write the structure, the bond moments due to these 3 chlorines, they are at 120 degrees dihedral angle. The bond moment due to these 3 chlorines is cancelled out. They cancel out each other. So whatever net resultant dipole moment it exerts, it is because of this chlorine. These 3 chlorines, they cancel out each other, and the resultant is due to this. So that is equal to 1.5 dBi. So the correct answer is third option, 1.5 dBi. Question number 31. Which of the following molecules has one unpaired electron in anti-bonding orbitals? The question is regarding molecule. So option 3 and 4 are ruled out because these are ions. CO is diamagnetic because it has even number of electrons and it has 14 electrons. It is diamagnetic. So the correct answer is NO. It has one unpaired electron, and this unpaired electron is present in pi star molecular orbital. So the correct answer is second option, NO. Question number 32. The compounds which contain ionic covalent and coordinate covalent bonds are: first option is ammonia, second option is ammonium chloride, third option is K3FeCN6 called as potassium ferricyanide, and fourth option is calcium carbide. And we need to find out the substance which has all the 3 types of bonds, ionic covalent and coordinate covalent bond. The options are: first option is B and C, second option B, C and D, third option is C and D, and fourth option is A and D. And the correct answer is, look at this. First, ammonia. Ammonia, it has 3 NH bonds, and all the 3 bonds are covalent bonds. Second option given is ammonium chloride. This is ammonium chloride. The attraction between NH4 plus and Cl minus is described as ionic bond. This is dative bond, and this is ordinary covalent bond. So this compound has all the 3 types of bonds: ionic bond, covalent bond, and coordinate covalent bond. Look at K3FeCN6. 3K plus and FeCN6 minus. This is 3 minus, and outside you will have 3K plus. So the attraction between these 2 species is ionic bond, and within this Fe is surrounded by 6 cyanide ions like this through dative bond. So it has dative bond also, and within cyanide Within cyanide, you have C triple bond N. These are ordinary covalent bonds present between C and N. So, between C and N, the type of bond is covalent bond. Between C and Fe, the bond is dative bond, and between FeCN6 and K plus, the bond is ionic. So, it has all the three types of bonds. Now, we are left out with another option, that is calcium carbide. Calcium carbide has this type of structure. So, between the carbon atoms, it has covalent bond, and you can say between calcium and carbon, the bond can be described as ionic bond. So, it does not have dative bond. So, the correct answer is first option, B and C. Question number 33. Which of the following molecules involve intramolecular hydrogen bond? A. Orthonitrophenol, compound B is chloral hydrate, compound C is paranitrophenol, and compound D is acetic acid. And look at the options. The correct answer is first option AC, second option CD, third option BC, and fourth option is A and B. We'll write the structures and try to find out which will have intramolecular hydrogen bond. The first compound given is orthonitrophenol. Look at the structure of orthonitrophenol. You have OH group, you have this NO2 group. Let's put it like this so that you can have formal charge and oxygen. So, there is a partial positive charge on hydrogen and partial negative charge on oxygen, and there is an intramolecular hydrogen bond in orthonitrophenol. So, this is one compound which can show intramolecular hydrogen bond. Look at second option, this compound B. Actually, this is compound A. The compound B is chloral hydrate. This is chloral hydrate. This has a partial negative and this has partial positive charge, and there is attraction like this. So, even this has intramolecular hydrogen bond. But look at compound C, OH, this is NO2 group. The groups are too far away to form hydrogen bond, they are too far away. Acetic acid, compound D is acetic acid. There is no chance of intermolecular hydrogen bond is possible, but intra is not possible. Intramolecular hydrogen bond is not possible. So, the correct answer therefore is fourth option, A and B. Question number 34. This is an assertion reason type of question. Look at the statement 1. Para-dimethoxybenzene has a dipole moment while para-dichlorobenzene has no dipole moment. The reason, the statement given for R is methoxy group is electron releasing and chlorine is electron withdrawing. Let's write the two structures. This is para-dichlorobenzene. The bond moment due to this is cancelled out by this. If this is minus, this is plus, so they cancel out, mu resultant is 0. Now, para-dimethoxy benzene, because here you have lone pairs on oxygen. So, bond rotation is possible here. Even here the bond rotation is possible. So, these two cannot cancel out each other. That is why it is polar. Mu r is not equal to 0. So, it is a fact that both methoxy group and is electron releasing and chlorine is electron withdrawing. This is a correct statement. So, both the statements are correct, but it is not a correct explanation for the statement 1. So the correct answer has to be second option. Both A and R are true. R is not the correct explanation of A. Question number 35. Again an assertion reason type of question. FeCl3 is more covalent than FeCl2. Ferric chloride is more covalent than ferrous chloride. And the reason: greater the charge on the cation, greater is the covalent character of the compound formed. This is true, and this is a correct explanation also. According to Fajan's rules, as the charge on the cation increases, covalent nature increases. Ferric has more polarizing power than ferrous. That's the reason why ferric chloride is more covalent than ferrous chloride. So the correct answer for this question is option 1. That is, both A and R are true, and R is a true correct explanation of A. Question number 36. This is again an assertion reason type of question. Orthonitrophenol is more volatile than paranitrophenol. Orthonitrophenol has intermolecular hydrogen bond, whereas paranitrophenol has intramolecular hydrogen bond. Look at the two compounds. This is orthonitrophenol. I am going to draw N dative bond. You can see the type of hydrogen bond you have here is intra, whereas paranitrophenol has NO2 group, para with respect to OH. There cannot be intramolecular hydrogen bond in paranitrophenol. In paranitrophenol, you can have intermolecular hydrogen bond, and intermolecular hydrogen bond increases boiling point. This has more boiling point than this. So the first statement is correct statement, that is orthonitrophenol is more volatile. More volatile means less boiling point than paranitrophenol. But look at the second statement. It says that orthonitrophenol has intermolecular hydrogen bond. It is not true. Ortho has intra and paranitrophenol has intermolecular hydrogen bond. So first statement is true, second statement is not true. So the correct answer is third point, that is A is true but R is not true. Third option is the correct answer for this question. Question number 37. Here again the assertion is beryllium chloride and xenon difluoride are isostructural. Yes, they are isostructural, both are linear molecules. The statement 2, that is reason given, is both have same hybridization. Yes, this is not true. While beryllium chloride has sp hybridization, xenon difluoride has sp3d hybridization. So the correct answer therefore is third option. A is true, R is not true. Look at the structure once again. BeCl2 has linear structure, there are no lone pairs. Xenon difluoride also has linear structure, but it has got 3 lone pairs on xenon. So altogether there are 5 electron pairs. That's the reason why hybridization of xenon is sp3d, whereas here it is sp hybridization. Lone pairs are present in equatorial position and the bond pairs occupy axial positions. So the correct answer is third option, which says A is true but R is not true. Question number 38. In which of the following pairs hybridization on the central atom is different? The first option given is ClF3, ClF3O. Second option ClF3O, ClF3O2. Third option ClF2O plus ClF4O minus. Fourth option is ClF4O minus XCOF4. The correct answer given is third option, that is ClF2O and ClF4O has same hybridization. Let us try to find out. ClF3 has 2 lone pairs and 3 bond pairs. So the hybridization is sp3d. ClF3O, it has 1 doubly bonded oxygen, 1 lone pair and 3 bond pairs of ClF bonds. So the hybridization should be 1, 2, 3, 4, 5 sp3d. So it is same hybridization. Look at this, ClF3O and ClF3O2. I'm going to draw ClF3O2. You can see chlorine is surrounded by 5 sigma bonds. So this is also sp3d. We don't take into account pi bonds, we take into account only sigma bonds. So these two have same hybridization. So option 2 is also ruled out. Let's look at option 3. ClF2O plus. Here we need to have we need to remove one electron. So we need to have 6 electrons around chlorine. We have accounted for 4. It needs to have one lone pair. So altogether we have 3 sigma bonds and one lone pair. So it should be sp3 hybridization, pyramidal shape. Whereas ClF4O minus, this will have 8 electrons around chlorine. Let's put 4 fluorines and a doubly bonded oxygen. 1, 2, 3, 4, 5, 6 electrons, and then it has to have one lone pair, because altogether you should account for 8 electrons. Now number of sigma bonds are 5 and number of lone pairs is 1, so it should be sp3d2. So that's the reason why third option is the correct answer. Whereas ClF4O minus is as good as XeOF4 because it has got one extra electron. So chlorine will be having 8 electrons around it, just like xenon has 8 electrons around it. So these two will be isostructural and have same hybridization. So the correct answer is third option, ClF2O plus and ClF4O minus will have different hybridizations, while ClF2O plus will have sp3 hybridization, ClF4O minus will have sp3d2 hybridization.